Hey guys, today we're going to look at how we define continuity in terms of limits and how to determine if our function is continuous. So in order to do this, what we're first going to do is fill out this chart here depending on this graph. And we're going to see if we can determine the three rules for our continuity. So for each column, you see that the first one gives us the x value. In the second column, we have to state whether the function is defined at that x value, and if so, we're going to write the function value. The next column, we're going to write out what is the limit of that function at that particular x value, and then we're going to determine if it is continuous. Now, if we have a graph, it's very easy to determine whether a function is continuous or not just by looking at it. If you have an asymptote, it is not continuous at that x value. And if you have a hole, it is not continuous. However, regardless of whether we have a graph or an equation, we will need to be able to prove why our function is continuous or not. So at this first x value, we have when x is equal to -4. And when we look at x is equal to -4, we have a hole, meaning that it is not defined. But if I try to calculate the limit as x is approaching -4, I do get an answer of 4. And if I look at the graph, is it continuous at this x value? It is not. So not continuous. Moving on to x is equal to -2. When I look at x is -2, I do have a defined value which is equal to 1. If I look for the limit, now remember that this is the general limit. So I'm looking at the left and the right, and they are equal to two separate values, so this limit does not exist. Now by looking at it, we can see that there is a jump discontinuity here since we have that vertical gap, so this is not continuous. At x is equal to 0, we see that our function does cross through the x is 0, and we get the y value, which is defined, which is 0. Our limit, as I go from the left and from the right, I do get the same value, which is 0. And we can see that it is continuous. Moving on to when x is equal to 1, since I have a vertical asymptote here, this function is not defined at x is equal to 1. When I try to calculate the limit from the left is infinity, the limit from the right is -infinity, so this limit does not exist. And as I mentioned earlier, because we have that vertical asymptote, this is not continuous. At x is equal to 3, we have the defined value, which is at 1. And if I try to calculate the limit from the left and from the right, we see that they are not equal, therefore this limit does not exist. This is another example of jump discontinuity, so this is not continuous. At x is equal to 5, I have the defined value, which is at -3. I have a limit value as x is approaching 5 of -2. And we can see here that this is considered a point discontinuity because I have a hole on the actual function and the defined value is somewhere else. So no, this is not continuous. As I look at my chart here, we only have one x value where the function is continuous, which is where x is equal to 0. Now what determines continuity? Well, first of all, your function has to be defined. So we would say that f of a is defined. And when we're determining continuity, we want to state what the defined value is. The second condition for continuity is that the limit must exist. So the limit as x is approaching a of f of x must exist, meaning that the left side and the right side do go towards the same y value. Now to determine continuity, we see when we compare the second column with the third column, that the defined value and the limit value are equal to the same number. And this is how we can tell that it is continuous, whether you have a graph or not. So that third condition of continuity is that your defined value, f of a, must equal to the limit value. So the limit as x is approaching a of f of x. So whenever we're determining continuity, we have to check off these three conditions. And if it fails the first condition, you don't have to continue, but you would say the function is not continuous because f of a is not defined, or you can say the function is not continuous because the limit does not exist, or the final one, the function is not continuous because f of a does not equal to the limit as x is approaching a of f of x. But if it is continuous, you would just state the function is continuous at x is equal to a because f of a equals to the limit as x approaching a of f of x. So now we're going to practice using this three-part definition of continuity. So first, remember you have to check for the defined value. So at x is equal to negative 3, I do have a defined value. So f of negative 3 is equal to negative 2. Even though I have the graph, I can tell that this is not continuous. I still want to go through my three-part definition so I can state exactly why it's not continuous. The second condition is that the limit as x is approaching negative 3 from the left of f of x. Oh, I'm sorry, this is g of x. Let me fix that. We must always be careful and write down exactly the function name correctly, whatever is given to us. So since this function is defined as g, I have to make sure that I use g of x in my analysis. So when I look at the limit as x is approaching negative 3 from the left, I do get negative 2. And as if I'm coming from the right, I get negative 1. Since these limits are not equal, that means that the limit as x is approaching negative 3 from the general limit does not exist. So I would write the limit as x is approaching negative 3 from the left of g of x does not equal the limit as x is approaching negative 3 from the right of g of x. So for my explanation, you would say g of x is not continuous at x is equal to negative 3 because the limit as x is approaching negative 3 of g of x does not exist. Now moving on to when x is equal to negative 5. When you look at x is equal to negative 5, we do have a defined value, which is at y is equal to 3. So g of negative 5 is defined and it equals to 3. Now we're going to find the limit. As you can see, at negative 5, the limit from the left does equal the limit from the right, and it equals to negative 3. So we would write the limit as x is approaching negative 5 of g of x is equal to negative 3. Now for our final condition, the defined value must equal to the limit value. And since they are not the same, that means that this function is not continuous. So you would state g of x is not continuous at x is equal to negative 5 because g of negative 5 does not equal the limit as x is approaching negative 5 of g of x, since it failed that third condition. Moving on to our last example here, we're trying to determine if the function is continuous at x is equal to 4. Now I can look at the graph and I do see that there are no holes and no jump discontinuities, no infinite discontinuities. So I know that it is continuous, but we still have to show all three conditions as being satisfied in order to prove that it is continuous. So the first condition, which is the defined value at x is equal to 4, and when I look at the graph, g of 4 is equal to 2. Additionally, I do see that the limit from the left and the right also equals to 2. So we would write the limit as x is approaching 4 of g of x equals 2. Since they are equal, that is our third condition, that means that the function is continuous at x is equal to 4. So we would write g of x is continuous at x is equal to 4 because g of 4 equals to the limit as x is approaching 4 of g of x. And this is how you were to prove whether your function is continuous or not continuous. You still have to show all of the work that goes before it. So it's always the same thing. You're finding your function value, you're finding the limit value, and then you are comparing whether the function value and the limit value are the same. Now for these examples here, what we're going to do is we're going to determine whether the function is continuous at the particular point that is indicated on this piecewise functions. These are a little bit different because now we don't have a graph. I can't just look at it and determine what the defined value is and what the limit value is. But we can still go through our same steps in the same manner. Now let's look at this first piecewise function. Notice the inequalities that are given to us. With a piecewise function, depending on those inequalities, that's going to tell you where there is a possible break of discontinuity, because that is where your function would end up changing. So for when x is less than -2, we would use this function. X is defined, the function is defined for when x is equal to -2, and we would use this particular function. And when x is greater than -2, we would use this function here. So our first step in determining continuity is to determine our function value. So we are going to test continuity for when x is equal to -2, because that is where my inequalities indicate that there could be a break in continuity. So we're going to start with f of -2, which is equal to, now our x is equal to -2 is defined here in the middle equation. So that's where I'm going to plug it in. So we would do 3 times -2 plus 2. And this gives me -6 plus 2, which is -4. Now we need to check that the limit from the left equals to the limit from the right. This first equation here, this is for when x is less than -2, so that is the limit from the left. So we're going to do the limit as x is approaching -2 of f of x, and we're going to use that top equation and plug in x is equal to -2. So we have -2 times the square root of -2 plus 6. When we work this out, -2 plus 6 is 4, the square root of 4 is 2, and then we have to multiply it with that -2, which gives us -4. So far everything is looking good because the limit from the left equals to my defined value. But I always need to double check, and I need to check the limit as x is approaching -2 from the right to make sure that this particular limit does exist. Now from the right, this is this bottom equation here because this is for when x is greater than -2. So I'm going to go ahead and plug it in there, and we get e raised to the -2 exponent plus the cosine of -2 pi. So now when I evaluate this, remember when you have a negative exponent, that means that e to the -2 is equal to 1 over e squared. Remember, a negative exponent basically moves your variable either to the denominator, or if you have a negative exponent in the denominator, you move it to the numerator. Now over here, we're going to add the cosine of -2 pi. Please remember that on your unit circle, here's 0. Now a negative angle means that instead of opening up, you're going to open down. And 2 pi is a full revolution. So we end up right back here where we started. And the coordinate there is 1, 0. Remember, the cosine is the x value. So the cosine of -2 pi would be 1. So now I get that the limit from the from the right is 1 over e squared plus 1, which is obviously not equal to the limit from the left, which is -4. Therefore, since this limit does not exist, that means that the function is not continuous at x is equal to -2. So we would state f of x is not continuous at x is equal to -2, and we have to state the reason why, which would be where it breaks the condition of continuity. which in this particular case, it broke that second condition because that limit does not exist. So we would state because the limit as x is approaching -2 of f of x does not exist. Now let's look at this second example. Again, we're always going to start with the defined value. And if you look at these inequalities, we see that we have one side for when x is less than pi, and the other one for when x is greater than or equal to pi. So that means that when x is equal to pi, there is a possible break of discontinuity. So what I'm going to check first is to find that function value for when x is pi. So we're looking for g of pi. Again, now when I'm looking at my inequalities, I see that pi is defined on this second equation. So I'm going to go ahead and plug in pi into this bottom equation. And that would give us e raised to the pi times the tangent of 3 pi over 4. When you're trying to evaluate the tangent of 3 pi over 4, keep in mind that 3 pi over 4 is in quadrant 2. And in quadrant 2, tangent is negative. When you look at your cosine values and your sine values at 3 pi over 4, which is right in the middle, this is 3 pi over 4, the coordinates there is the square root of 2 over, negative square root of 2 over 2 over square root of 2 over 2. Tangent is the sine value divided by the cosine value. And if you divide the square root of 2 over 2 by negative square root of 2 over 2, you would get 1. So therefore, negative 1. Therefore, g of pi is e raised to the pi times negative 1, which is equal to negative e raised to the pi. So that's my defined value. Now I'm going to check for my limit values. So we're going to start with the limit as x is approaching pi from the left of g of x. Now from the left, we see from the inequalities that x is less than pi using this first equation. So that's where I'm going to plug it in. And that would give me e raised to the pi times cosine of pi. Now cosine of pi is over here on the negative x-axis. That is the coordinate -1, 0. My x value is the cosine. So that means that the limit as x is approaching pi from the left of g of x is e raised to the pi times -1, which is equivalent to negative e to the pi. Now if I need to calculate the limit from the right, we can look over at my inequalities and I see that the limit from the right is the same equation as the defined value. Therefore, I don't necessarily need to find this additional limit because it is the same work that we concluded here. And the limit from the right would also equal to negative e raised to the pi. So what does that mean? That means that my general limit is negative e to the pi since it's the same as the left side. My defined value is negative e to the pi. So therefore, my function is continuous when x is equal to pi. So we would state g of x is continuous at x is equal to pi because g of pi is equal to the limit as x approaches pi of g of x. So what we've been doing up to now is we've been determining whether the function is or not continuous. What we're going to do now is we're going to look at a function, and the function is going to give us a few variables, such as here you see m and k. Now these are not necessarily variables, but represent constants. And what we want to do is figure out what those constants would be so that this particular function would be continuous everywhere. So we're going to take this piecewise function and make it continuous. So in order to do so, we see that all of these x values here are defined somewhere. So we do have defined values. What's most important for these is to make sure that the limits are equal. And that's what's going to guide our answer in the end. So I broke this question down into 3 parts. First, we're going to write down what 2 limits must be equal in order for f of x to be continuous at x is equal to -1. Now I say -1 because when we look at our inequalities here, we see that there could be a possible break of discontinuity when x is negative 1, as well as when x is equal to 3, which is what we're going to do afterwards. So here we go. In order for us to determine when the limits are equal for when x is equal to negative 1, we would state, just as always, for a limit to exist, that means that the limit from the left must equal the limit from the right. Now when you look at this doesn't really help me do anything, but this is how we set up our answer, or rather our work. Okay, so since I have the limit from the left must equal the limit from the right, what I'm going to do is I'm going to look at my piecewise function. I'm going to look at the left side of negative 1, which is right here. See, this is for when x is less than or equal to negative 1, and the function value is 2. So that's the left side, and it must equal to the right side. See, here in the middle, we have when x is greater than negative 1. So that means that is the right side of negative 1. So we make 2 equal to mx plus k. We're going to set that aside for now. We're going to take a look at the following question. What two limits must be equal in order for f of x to be continuous at x is equal to 3? Again, we follow the same logic, right? So for any limit to exist, that means that the limit as x is approaching 3 from the left of f of x must equal the limit as x is approaching 3 from the right of f of x. And if I were to look at my piecewise function, I can substitute those limits with the function. So the limit from the left as x is approaching 3 is here in the middle. See, it says x is less than 3. That is to the left of 3. So mx plus k, that's the left side, must equal to the right side, which is when x is greater than or equal to 3. So it must equal to negative 2. Once you have set up your limits and you've substituted those limit values with your equations, what we can now do is plug in the x value for each one in order to get a more precise equation in terms of m and x only. M and k only, so that way we can use it to solve for m and k. For this particular statement, this was written for the limit as x is approaching negative 1. So I'm going to plug in negative 1 for the x. So this equation would read 2 is equal to negative m plus k. And this one here, this equation was written from the limits as x is approaching 3. So I'm going to plug in x is equal to 3 into x. And that would give me 3m plus k is equal to negative 2. Now, since I have two constants here that I'm trying to solve for, think of them as your variables, we're trying to solve for m and k. Since I'm solving for two separate variables, that means that I need two separate equations to solve for them, which is what I have. I do have two equations, and we can determine that, and we can create a system from those two equations. So we have this negative m plus k is equal to 2. That is my first equation. I just rewrote it so that m and k are on the left side. And then we have this second equation, which is 3m plus k, which is equal to negative 2. And now I can solve this system using whatever method you prefer. In this particular case, I'm going to use the elimination method because I do see that k's here could cancel out if I multiply one of those equations by negative 1. I'm going to choose to multiply the top equation by negative 1. And what that would leave me with is a positive m minus k is equal to negative 2. And then my second equation, which is 3m plus k, is equal to negative 2. When I combine these, I get 4m is equal to negative 4. And so then I can solve for m by dividing the 4. And I get that m is equal to negative 1. Now that I have m, I can plug it into whichever original equation and solve for k. I'm going to plug it into the 3m plus k is equal to negative 2, but it doesn't matter if you choose to plug it into that first equation. So 3 times negative 1, which is the m that I found, plus k is equal to negative 2. this would leave me with -3 plus k is equal to -2. And then to solve for k, I would just add the 3 to both sides, and I get that k is equal to 1. So my two values here, in order for f of x to be continuous, m would have to equal to -1, and k would have to equal to +1. Let's try another example. Okay, for this example, we have g of x, and then when we look at these inequalities, I see that there's a possible break of continuity when x is -2 and when x is 3. So those are the two values we're going to use when we're writing our limits, and we're trying to make this function continuous and to solve for k and m. So first, we're going to start with when x is -2. I'm going to set up my limit. So the limit as x is approaching -2 from the left of g of x must equal the limit as x is approaching -2 from the right of g of x. Now that I've set up my limits, I can replace those limits with our actual function. For the left side of -2, we look at our piecewise and we see that x is less than -2, and we use this part of the function. So kx² plus m equals to, now x is greater than -2, that means that's the right side of -2, which is 4x plus 1. Now that you've substituted your limits with the actual function, we're now going to plug in that particular x value, which is x is -2. So when I plug it in, we would get k times -2 squared plus m, which equals to 4 times -2 plus 1. When you simplify this, -2 squared is 4k plus m, and that's going to equal to -8 plus 1, which is -7. So now that I'm done with that one, remember that this is an equation you're going to have to come back to. So if you need to, you can always put a little star by it, so that way you know that this is your equation. Now we're going to look at the second limit statement, and we're going to use for when x is 3. So the limit as x is approaching 3 from the left of g of x has to equal the limit as x is approaching 3 from the right of g of x. Now that you've set up your limit statements, we can substitute those limits with the actual function. The limit as x is approaching 3 from the left is defined here, because this is where x is less than 3. So we're going to use the 4x plus 1, which is going to equal to when x is greater than 3, because that's the right side, which is defined to be kx minus m. Now that you have your equation set up, you can plug in that corresponding x value, which is 3. When you plug it in over here, you get 4 times 3, which is 12, plus 1, so 13, is going to equal to k times 3, so 3k, minus m. This is your second equation. Now that you have your two equations in order to solve for k and m, you can go ahead and set up your system. When you write out your systems, you always want to make sure that your variables are lined up. So I'm going to write this first equation, 4k plus m equals -7. And the second equation I'm writing as 3k minus m is equal to 13. And you can choose whichever method you prefer here in order to solve, either substitution or elimination. For this one, I see that m, both positive and negative, would cancel out if I were to use the elimination method. So I can cancel these, and that would give me 7k is equal to 6. Divide the 7, and you get a value that k is equal to 6 over 7. Now that you have k, you can plug k into any original equation to solve for m. So I'm going to go ahead and just plug it into the 4k plus m equals -7. So 4 times k over 7 plus m is equal to -7. When I multiply 4 times 1 over 7, remember it's numerator with numerator, denominator with denominator. This is 24 over 7 plus m is equal to -7. To solve for m, we're just going to subtract that negative 24 over 7 to the other side. Remember, in order to subtract, you are going to need a common denominator. So if I put this negative 7 over 1, my common denominator would be 7. So I'd have to multiply both the numerator and the denominator by 7, which gives me m would equal to negative 49 minus 24, and it's all over 7. When I subtract, I get negative 73 over 7. And that is your value of k and m in order for your function g of x to be continuous all throughout.